Mr. Prof. Good morning. Morning. Thank you. Nice to meet you.
We do have a next she built up
especially with Stephen.
Yes. Of course, I think there's
a small Jesuit Philippine, a small
Anyway, you was interested that they modified.
Let me ask the Dominican Spanish essentially.
Ladies and gentlemen, good afternoon. I'm Dr. Roland Hurtado, Chair of the Department of Physics. It has now begun the press conference. Then of the University of San Carlos, Dr. Uwe Morawetz, founding chairman of the International Peace Foundation, Professor David Jonathan Ross, 2004 Nobel Laureate for Physics.
Last year, and we have to credit Mr. Uwe Morawetz, who is here, for bringing over the project bridges to the Philippines beyond Thailand. That will be explained in a little more detailed way later. But just as a background, Thailand had hosted a series of lectures by Nobel laureates. And so after those series of lectures in Thailand, the foundation thought that we should go beyond the borders of Thailand. That's why last year was an exploratory year. Dr. Uwe came around, met some of our universities in the Philippines, and explored ways how we could bring over to the Philippines, to Cebu. University of San Carlos is hosting. The second one will be in February. But this is the very first one. And this is the first one outside Manila in the Visayas. Most of the lectures are held in Manila, will be held in Manila. Outside Manila, in Mindanao, it's only Ateneo de Davao. In the Visayas,
in breaking the ice. So, because just to explain a little bit more, bridges, what does it mean and why do we do this? Because normally when Nobel laureates visit Asia, they go to China, they go to Japan, to South Korea, or to Taiwan, but very seldom they visit countries in Southeast Asia. So, our foundation, the International Peace Foundation, which is actually based in Vienna, but with an Asian office in Bangkok, believes that the basis for peace is education. This is why we want to bridge people who won the Nobel Prize and their institutions, normally in the West, with the universities here in the Philippines. And almost all of the Nobel laureates we are bringing here, there are 6 from different fields, plus James Wolfenson. They have never been here before. And we really would like them to learn more about the institutions here, to hopefully, in the long term, build relationships with these universities which are sustainable, that maybe in the future more Nobel laureates will visit the country, share their knowledge and their experience with the scientific and the educational community in the country. But also maybe to start research programs with the universities. Many of the Nobel laureates we brought to Thailand since 2003 now return regularly. So this program is not a one-time event. It's a continuous series now, started in November last year until April, with about 50 events taking place here in the Philippines. And next year the program will go to Malaysia. So every year we have been invited now by another country to do these bridges programs. Malaysia will be then followed by Cambodia, Vietnam, Singapore, Indonesia, Laos and Brunei. So, and it will end in the year 2015. If not by then, Myanmar is a democratic country. So then we might expand to Myanmar or maybe also to East Timor, and it's a member of ASEAN.
All in the domain of experimental physics.
So for those of you who know little about string theory is a very ambitious attempt to construct a unified theory of all the forces of nature and all the constituents of matter. And it's actually been, people have been working on string theory for now 40 years. And I believe we're still somewhere, if we're lucky, in the middle of the development of this theory. We even understand what string theory is. In string theory could appear cosmic strings stretched across the galaxy. That would be direct experimental grasp on string theory. But if we're not lucky, it might take a long time before we truly develop the theory to the stage where we can make contact with experiment. However, there are elements of our speculation, new symmetries of nature that came out of string theory and are an important part of it. In particular, something called supersymmetry, which we hope to find evidence for in the next few years, as soon as the Large Hadron Collider, an immense particle accelerator, opens and starts doing research in Geneva and CERN this year. So we have a lot of hope for...
What is the impact of physics towards the culture of peace?
You know, physics, there are direct applications of science in general, and physics in particular, to modern technology, which can help us and hurt us. can be used in different ways, but it certainly can help us in solving many of the problems that face the world. But I also value a lot the indirect influence of science in general, and the scientific culture on lifting ignorance from the world and promoting cooperation between nations. And physics is, especially, but all the sciences are an incredibly collaborative international effort. So after the war, for example, the accelerator I spoke of before, the LHC, which we're waiting for, is located at the European Laboratory of Physics, that was started right after the war by physicists in Europe, and it was the first organization that brought together European countries to work together.
Environment really needs, and really energy and environmental economists. Taking off from the question about peace and physics, and the politics of science, what can you say about this question of the proliferation of nuclear weapons and the fact that there seems to be a lot of ambiguity about whether this country is pursuing a weapons program or not, and who are the accusers and what their objectives are. You as a scientist and physicist, and I know of many physicists in the past who have been actively campaigning against nuclear weapons and for denuclearization. Where do you stand, Dr. Prof?
It's a very good question, because most people nowadays, most people have forgotten about the enormous danger that nuclear weapons still pose to the survival of mankind. I mean, when I was a child, we learned in school to, if we heard, the siren, to get under the desks, but that the young people today barely know that the world is still armed. The superpowers in half an hour could destroy all life on Earth. And that threat has not disappeared. And there are a lot of people to blame, and the superpowers mostly, for not taking this opportunity now to reduce, if not eliminate, but certainly reduce by a factor of 100 the number of nuclear weapons ready to be launched within hours. And in the absence of such action on the part of superpowers, and the proliferation of nuclear weapons is inevitable. So the first blame is Russia, the United States especially, and all the heavily nuclear-armed countries, which like the status quo. But it's going to be very hard to stop proliferation. We can see it happening. It's extremely dangerous. And people should be demanding that their governments eliminate these stupid weapons. These are weapons that have no point. They can never be used without disaster. They should be eliminated. People around the world are scared about building nuclear energy plants, which are very clean, and we know how to build them safely. They're scared of a little bit of radiation being emitted sometimes in accidents, or once, Chernobyl, a lot of radiation. But they seem to not to make 1,000 Chernobyls and designed to be exploded over cities. We still have these awful things. So I think it's a scandal that we haven't yet dealt with it, and the danger remains and is high, and we have to really increase the awareness of the general public.
Nuclear fusion as a source of power.
Well, years ago, nuclear fusion was the wonderful hope of mankind, but it was a long time away. 50 years, they said. And today they say nuclear fusion is a wonderful solution to our energy problems, and it's 50 years away. So it always seems to be 50 years away. It's a very hard problem. So we now are, there's a big international collaboration of most of the industrialized countries building almost a prototype engineering facility located in France called ITER, which is the next step towards developing a fusion facility. But it's still a long time away. And so we all hope that the engineering problems, and they're mostly now engineering problems, to build a fusion, to tap the energy in hydrogen and deuterium to create clean, renewable power will be realized sometime, but it's not going to help us in the short run, the next 50 years. It will have no impact. Even if the plans come along, there'd be such a massive effort that they could barely touch the energy budget. So for the next 50 years, they're irrelevant.
Professor van Engelen, I may introduce myself as a physicist, but then a subsistence physicist. If you understand the connotation. On the other side, I remain interested in physics, also the large scale. If I'm not mistaken, it was 1 or 2 years ago that there was a flash observed in our galaxy, a fantastic source of energy. I suppose that you know which one I am talking. That was reported in general terms by astronomers. But is that a signal of an additional unknown source of energy? Because it seems to have been a fantastic explosion, instant, very short, milliseconds, of an energy where we apparently don't have any idea of what that might be. Is that true? That there is perhaps there something that was happening beyond an hydrogen?
Yeah. There are many such bursts of energy that are observed. They're called energy, and it's deduced, at least, from the flash that we see. But gamma ray bursts are believed to be quote-unquote understood. In other words, we have explanations which seem realistic now, having to do with exotic objects like black holes, but still physics that we sort of understand. And so in the beginning, when gamma ray bursts were first discovered, the beginning when quasars were first discovered, people had thought that they might be signs of physics beyond the physics that we understand, atomic physics, nuclear physics, the physics that I worked on in the nuclear force and gravity. But mostly it's turned out that although sometimes black holes are involved, which are pretty exotic objects, these things have normal explanations. And I think the consensus, at my institute we had a program on gamma ray bursts about 2 years ago, and the consensus was that the spectrum of, one can understand these incredibly intensive things. Now, are they new sources of energy? Therefore, probably not. If we had a nearby black hole, which might be quite dangerous for us, we could use it maybe to extract energy, but unfortunately they're not available. We've only had one member of the press who is courageous enough to ask a question.
Ross, one of your prestigious predecessors as a Nobel laureate, Murray Gell-Mann, has, I think, made attempts to popularize some of the work he did in physics in terms of complexity theory. And what I'm referring to is Quark and the Jaguar. What is the usefulness of this type of work?
Well, complexity theory, chaos theory was very popular about 20 years ago when Murray was heavily involved with that. You know, physicists tackle easy problems first. That makes a lot of sense. It's not obvious. Galileo really was the first to understand that before you start asking hard problems about complicated systems, first you should understand how a pendulum works, even though it might not seem that interesting. So, for what we understand best are systems in equilibrium where nothing much happens, in steady state. But many of the systems in the real world you have observed, right, from your own observations, are much more complicated and chaotic and irregular, and like the weather, and harder to predict. And we don't understand them as well. And from time to time, new methods, new ways of thinking are pushing us to try to tackle these very hard problems. Turbulence, or chaotic behavior, irregular behavior that looks random, but actually has, we believe, have evidence for hidden structure, which we should be able to figure out, and then maybe be able to predict the weather with much more certitude. And about 20 years ago, there was a big resurgence. There were some very wonderful new ideas in the theory of chaos and in the theory of complex, non-equilibrium phenomena. And people at that time, as usual in physics, when new discoveries are made, new understanding is developed, go a bit overboard on how revolutionary and how important and how great they are, and that's what happened 20 years ago. A lot of excitement that this would enable us finally to crack all these hard problems and predict next week's weather with certitude. But it didn't happen. So, first of all, there's someone here who hasn't had a...
Good afternoon. I'm Nancy from Sunstar. Sorry, in the UK, physicists are circulating a petition against the Science and Technology Facilities Council over budget cuts that are likely to affect research in particle physics and astronomy. Is funding also a concern in the scientific community in the United States? And if so, how have they dealt with it?
Yes, well, there have been two disasters, budgetary disasters in the West in the last 2 months. One was in England, which you're referring to, where they consolidated big science and little science in one agency. And this turned out to be a disaster because they, instead of putting the budgets together, they squeezed the budgets and lost quite a bit. And of course, big science, you know, there are many more people doing little science than those doing big science. So big science projects are often under criticism and by the community that these funding agents, by a large majority of the community that these scientists, that these agencies support. And under such budget crunches, they decided to cut in a very dramatic way their involvement in a whole bunch of projects, big science projects, including ITER, the fusion project, not ITER, Gemini, an astronomy project, the particle physics project, the International Linear Collider, and so on and so on. It was a tremendously dramatic move. What it probably was, politically, was an attempt to get the government to restore the money. It was so crazy a decision that it could only be interpreted as a way of putting pressure on the government to return the money that they've taken away. But it is illustrative of the fact that it is politicians are not the best scientific administrators in the world, to say the least. The same happened in my country in this budget round where we have a Congress which is controlled by the Democrats and the president fighting over the budget, and in that process science doesn't matter very much compared to other items which are of more interest to politicians. So again, there was severe budget cuts of a build-up in the physical sciences which had been planned for years and was just beginning to take place. Dramatic cuts occurred for purely political reasons, which are extremely dangerous. So it's an illustration to us scientists that the political process in a democracy is not necessarily, has a lot of problems dealing with a careful, multi-year, thoughtful process that is necessary for the healthy development of science. So we all have problems.
Shall we have the last question from you, sir?
The question is also addressed to Dr. Morawetz. Bridges, dialogues towards the culture of peace. Isn't there also, to some people's minds at least, a clash of cultures, which makes this peace very elusive? And on another plane, still on a clash of cultures, do you think there is a fundamental conflict between science and religion? Don't be afraid of Father Salazar because he's a very open-minded fellow. So.
Maybe not to religion, but the way maybe religion is misused for. But I think we believe, we live in a very, in a world where politicians speak another language than people from religion. They speak another language than scientists. They speak another language than artists. They speak another language than business people. And we live in a very interconnected world. And very often politicians claim maybe to have the answers for solutions, or other groups of societies. So we normally don't come together, or don't speak with each other, or don't work together. And so we cannot offer any solutions how to achieve peace, but hope that out of these dialogues there will be questions that hopefully lead to solutions in the end. And also in universities, very often students are taught answers, but not how to ask questions. So, and we'd like to be an open forum, and from which maybe solutions which we cannot think of today can emerge.
Okay, that is the end.
Reverend Father Roderick C. Salazar Jr., SVD, President of the University of San Carlos. Reverend Father Roderick C. Salazar Jr., SVD, President of the University of San Carlos. Dr. Uwe Morawetz, founding chairman of the International Peace Foundation. Ladies and gentlemen, our speaker, 2004 Nobel laureate in physics, Professor David Johnson. audience, distinguished guests, Professor David Jonathan Ross. I am Melba Rodriguez Hava, and I shall guide you this afternoon through this ceremony. Let us begin with an invocation to be led by Father Teodoro P. Gapus, SVD, Vice President for Academic Affairs. And please remain standing for the singing of the Philippine National Anthem to be led by the USC choristers.
Under the auspices of the International Peace Foundation's initiative, Bridges, Dialogue Stirs a Culture of Peace, we have come together today in Cebu City, in the University of San Carlos, to a dialogue with our Nobel laureate in physics, Dr. David J. Gross. As we interact on a slice of reality, a dimension of creation, we honor the greatness, the immensity, and the wisdom of the Creator. In the spirit of that beautiful poem of Cecil Frances Alexander, which most of us are familiar with in grade school, let us exalt with her all things bright and beautiful, all creatures great and small, all things wise and wonderful, the Lord God made them all. And so in prayer then, let us with our hearts and minds join the psalmist in the book of Psalms in the Old Testament. Alleluia. Let the heavens praise Yahweh. Praise Him, all His angels. Praise Him, all His armies. Praise Him, sun and moon. Praise Him, shining stars. Praise Him, highest heavens, and waters above the heavens. Let them all praise the name of Yahweh, at whose command they were all created. He has fixed them in their place forever by an unchangeable statute. Let the earth praise Yahweh, sea monsters and all the deep, fire and hail, snow and mist, gales that obey His decree, mountains and hills, orchards and forests, wild animals and farm animals, snakes and birds, all kings of the earth and nations, princes, all rulers in the world, young men and young women, all people and children too. Let them all praise the name of Yahweh, for His name and no other name is sublime, transcending earth and heaven in majesty, raising the fortunes of His people to the praises of His devout people, the people dear to Him. And so we close our prayer to the Creator with the last words of the same poet. He gave us eyes to see them and lips that we might tell how great is God Almighty, who has made all things well. Amen.
Thank you, Father Gapus. Ladies and gentlemen, the Philippine National Anthem.
Bayang mag-iiw, sa silangan, hindi kaya na pa, may mga api ang mamatay na dahil sa'yo.
Thank you, and please be seated. Roderick C. Salazar Jr., SVD, the University President, will now give the welcome address.
Good afternoon, ladies and gentlemen.
Good afternoon.
Carolinians and friends of Carolinians. Welcome to our University of San Carlos, to this lecture of an esteemed authority in the person of Professor David Jonathan Gross, 2004 Nobel laureate for physics. It is a rare privilege for our city, province, island, and our own university to host such an event as this. In fact, as far as I know, this is the first time ever that we are hosting a lecture by a Nobel laureate in whatever field. Thus, on behalf of all of us who are here, I thank Mr. Uwe Morawetz for the generous act of extending the program bridges beyond the borders of Thailand to our own beloved country. And I thank him for choosing the University of San Carlos to represent Visayas as the host for the lectures outside of Manila. And of course, we thank Dr. Gross himself for accepting the invitation to come. Welcome to you, sir, to your wife, and to the party of Dr. Uwe Morawetz. We are, as you know, at the University of San Carlos, an educational institution that traces its roots to a school founded in 1595. That our religious congregation, the Society of the Divine Word, took over in 1935. And that officially became University of San Carlos on July 1, 1948. Thus, we are in our 60th year as university, which some already consider a diamond anniversary. So what better way is there to mark the beginning of this blessed year with this lecture by our esteemed Dr. David Jonathan Gross. So we are gathered here today from different sectors of civil society, the academe, the government, the media, civil society, all of us here. The Coming Revolutions in Fundamental Physics is the official title of the presentation today. We should soon know why, and may we emerge from this lecture better informed and richer, not only because of what we shall hear, but even from the mere fact of our being together today. Without pretending to be a physicist, which you all know I am not, I suggest that maybe we could prepare ourselves for the lecture by recalling some of the physics laws and principles we may have learned in school. For instance, Newton's law. You will remember what that was, what that is. When a third grader was asked to cite Newton's first law, she said, bodies in motion remain in motion, and bodies at rest stay in bed, unless their mothers call them to get up. So we are here because we or our mothers call us to get up. And I welcome you that you are here. We recall other principles. 3 graduate physics students, I don't think they came from University of San Carlos, or maybe they did. They sought to demonstrate that a human could travel faster than light. So they went to a store and bought a stopwatch and a candle. Then they proceeded to a high school track field. The first student lit the candle and began to walk around the track. The second student waited a while and then ran after the first student. The first student worked the stopwatch because, you should know, physics experiments require precise measurements. And when the second student rounded the track and came in first, the three students concluded that humans could travel faster than light. I suppose you can have better conclusions than that, but it's a way of recalling what we may have learned years ago. And I'm not sure if Albert Einstein himself would approve of that kind of experiment. But about him, there is a story. Perhaps remember that at least that C is the symbol for the speed of light. We may not know this attempt at explaining why Einstein used this symbol. The story goes that Albert Einstein had just about finished his work on the theory of special relativity when he decided to take a break and go on vacation to Mexico. So he hopped on a plane and headed to Acapulco. Each day, late in the afternoon, sporting dark sunglasses, he walked in the white Mexican sand and breathed in the fresh Pacific sea air. On the last day, he paused during his stroll to sit down on a bench and watch the sun set. The large orange ball was just disappearing. A last beam of light seemed to radiate toward him. He then brought him back to thinking about his physics work. He asked himself, what symbol should I use for the speed of light? The problem was that nearly every Greek letter had been taken for some other purpose. Just then, a beautiful Mexican woman passed by. Albert Einstein just had to say something to her. And almost out of desperation, he asked as he lowered his dark sunglasses, do you not think that the speed of light is very fast? The woman smiled at Einstein, which, by the way, made his heart sink. But the Mexican woman replied, "Sí." And now you know why C is the symbol of the speed of light. But I'm told that Einstein's favorite limerick goes, there was an old lady called Bright who could travel much faster than light. She departed one day in a relative way and returned on the previous night. Now, with this little review of some basic physics principles, I suppose we should be ready for the lecture after we hear the explanation of why we are here in the first place. In the meantime, thank you for being here. Welcome to the University of San Carlos. Let's enjoy the afternoon.
Reverend Father Roderick Salazar, President of the University of San Carlos. Now to explain to us the rationale behind the Bridges program, let me call on the founding chairman of the International Peace Foundation, Dr. Uwe Morawetz.
And welcome to the first ASEAN event series, Bridges, Dialogues Towards a Culture of Peace. Bridges is facilitated by the International Peace Foundation, a non-political and non-religious foundation under the common patronage of 21 Nobel Peace Prize laureates based in Vienna. The events are hosted in cooperation with various local partners, including the country's major universities, and I thank the University of San Carlos and its president, Father Salazar, for hosting our event today. Having started in November 2007, Bridges is being continuously held in the Philippines and Thailand until April 2008, involving the participation of Nobel laureates for peace, physics, chemistry, medicine, and economics. The first ASEAN series of bridges is an independent contribution to the Decade for a Culture of Peace and Nonviolence, initiated and promoted by the United Nations General Assembly. It follows the series of 250 bridges events, which the International Peace Foundation has already hosted in Thailand between November 2003 and April 2005. 26 Nobel laureates, as well as 12 other keynote speakers and artists, such as Dr. Hans Blix, the Reverend Jesse Jackson, Vanessa May, and Jessie Norman, participated in these events. They were presided over by Her Majesty Queen Sirikit and Her Royal Highness Crown Princess Mahashakri Sinitorn, and reached an audience of 70,000 participants. As peace cannot be achieved instantly, but is a process which needs time, Bridges has not been organized as a single conference, but as an ongoing series of events in which Nobel laureates and international decision makers have built strong bridges with leaders in all parts of society and with the general public. With the basis for peace being education and synergies being the fruit of cooperation, the International Peace Foundation hasn't realized bridges alone, but has carried out the program together with UNESCO and 75 other national and international institutions, including 23 major universities and schools. The multidisciplinary and pluralistic approach of bridges in Thailand and of the events in the Philippines reflects that peace involves all parts of society. It involves awareness and social responsibility of politicians, the business community, scientists, artists, and the media. And since peace within ourselves, our families, and the environment starts in our minds and hearts, it involves every one of us. In this sense, Bridges challenges us to cross borders and to build bridges by listening and opening up to other viewpoints, by generating new thoughts, by developing innovative forms of cooperation, and by fulfilling the desire of everyone to get to know and to learn from each other. This can lead us to a world in which we will be able to understand each other and the complexities we face today in a new light. The globalized world needs broad strategies for change, to secure a sustainable future for us and the next generations. Let us be inspired by the knowledge and the wisdom that Bridges continues to offer. An opportunity to get a more inclusive, interconnected, and comprehensive view of ourselves and the world in which we live in which we are able to create anew constantly, through dialogues towards a culture of peace, which needs the participation of everyone. I thank Professor David Gross, the 2004 Nobel laureate for physics, who has agreed to come to the Philippines without any honorarium to support the events, and we now look forward to his keynote speech and to his important contribution to build bridges. I'm very sorry I cannot speak Filipino, but I like to say maraming salamat po sa inyo.
Thank you, Dr. Morawetz. Dr. Christopher Bernido, Director of the Research Center for Theoretical Physics at the Central Visayan Institute Foundation in Hagna, Bohol, will now introduce the speaker.
Reverend Father Roderick Salazar Jr., President of the University of San Carlos. Dr. Uwe Morawetz, Founding Chairman of the International Peace Foundation. Professor David Gross, 2004 Nobel Prize winner in Physics. Distinguished guests, ladies and gentlemen, good afternoon.
Good afternoon.
It is indeed an honor for me to introduce our distinguished lecturer this afternoon. Professor David Jonathan Gross was born in Washington, D.C., in the USA. He obtained his undergraduate degree from the Hebrew University in Jerusalem in 1962. He then went back to the US and took his graduate studies at the University of California at Berkeley, working under the supervision of Dr. Jeffrey Chu. And he obtained his PhD in 1966. He then moved on and went to the East Coast as a junior fellow of the Harvard University. And in 1969, he joined Princeton University. In 1972, he was appointed as professor of physics at Princeton University, working at the Joseph Henry Laboratories. And in fact, it was around at this year, in 1972, that together with his graduate student Frank Wilczek, they tried to prove that there is no asymptotically free field theory. But given the power and logic of mathematics and physics, they found out the opposite. And so that was the beginning of the asymptotic freedom feature of strong interactions. And they published the result about non-abelian gauge theories being asymptotically free the following year. There was some sort of a euphoria in the particle physics community right after this result was published. And of course, it earned him, together with Frank Wilczek and David Politzer, the Nobel Prize in Physics in 2004. Professor David Gross has received numerous awards. Among these would be the J.J. Sakurai Prize, given by the American Physical Society, the prestigious MacArthur Foundation Fellowship, the best or the highest award given by France, scientific award given by France, the Grand Médaille d'Or. He has also been given the Harvey Prize of the Technion, and numerous other prizes. I had the lucky opportunity to have listened to Professor David Gross several times before. One was in 1988 in Kazimierz, Poland. There was this conference in New Theories in Physics. The other occasion was the inaugural conference of the Asia Pacific Center for Theoretical Physics in June 1996 in Seoul, Korea. And somewhere in between, a lecture given at the International Center for Theoretical Physics in Trieste, Italy, from which he also got the Dirac Medal. To my mind, Professor Gross is one of the most dynamic and powerful speakers that I have seen and heard amongst the Physics Nobel Prize winners. So ladies and gentlemen, let us now listen to Professor David Gross to give his lecture on the coming revolutions in fundamental physics.
Well, thank you, Dr. Benito. Thank you, President Salazar. And good afternoon. Good afternoon. So I was originally going to talk, as advertised, about the coming revolutions in fundamental physics. That's a talk about elementary particle physics, string theory, and what awaits us. But that talk takes about an hour and a half and requires a little more background than that presented to you by President Salazar. So instead, I'm going to talk about a broader subject, the lessons of science. Will be both the obvious lessons of science and those that might not be so obvious. First, I'll talk about the scientific method, this new way of thinking that was discovered at about the time this university was founded, 400 years ago, and has proved so fruitful in discovering the secrets of nature and making use of them. I'll also stress the importance of lessons that we can learn from the scientific method that might be applicable to other areas of human discourse and human engagement. Then I'll talk about the actual product of science, which of course, at first, is the knowledge we gain of natural phenomena, of the workings of the universe. And of course, that knowledge is often applied, so I'll say a word about the incredible control that we have already achieved over nature using the tools of science. The incredible benefits to mankind that have emerged from this, and some of the unfortunate dangers that face us because of our technological advances as well. And then I'll turn to one of the ways in which I think we're going to have to move in order to solve some of these problems that face our world. Not just better science to gain better and wiser control of nature, but also better instruments of cooperation and collaboration, internationalism. And I'll use science as an example of international cooperation and collaboration. And I'll end, as a scientist should, with the questions, the examples of the questions that will propel science forward in the future. And since my business as a theoretical physicist is to make predictions, I will make some predictions. So let me start with the scientific method. The scientific method is a way of thinking about the world, a strategy to learn about the natural phenomena that was not obvious. In fact, it took thousands of years to discover. And it really has only been a strategy that has been employed by thinkers in the last 400 years. It's based primarily on the idea that understanding of natural phenomena is obtained always by subjecting our ideas to observation and experiment. We observe, we carry out experiments, we form models and ideas based on observations and experiment and our own imagination. But we must subject those ideas to observation and to experiment. And in fact, the only authority for truth, according to the scientific method, is agreement with nature by means of observation and experiment, not political power or religious faith. Parliaments cannot repeal the law of gravity. And all of our theories, all of our basic concepts are, we suspect, provisional. Science promotes skepticism. We have learned the hard way that there are no absolutes. Is it possible to have a little more sunlight on the audience? I'd like to see who I'm talking to. A little bit of light as we had before. Is that all right? So we've learned that all of our concepts are provisional. All of our theories are provisional. And they're subject to continuing questioning, challenges, tests, and eventually, as we've learned, improvement. And finally, we've learned that everyone can make contributions to scientific advances, and that to have an efficient scientific enterprise, we must open up scientific inquiry to all, and scientific findings must be made available to everyone. This is also a rather modern idea. In the Middle Ages, scholars would making scientific discoveries would keep them secret or express them in anagrams so that their competitors wouldn't learn what they're doing. But that has proved to be very inefficient, not useful. And we've developed lots of ways of rewarding scientists by prizes, for example, so that they are willing to make their findings immediately available to anyone in the world. That's a very important aspect of research, certainly in the basic sciences. These lessons we have learned and methods of inquiry and research that we have perfected over the last 4 centuries have implications which go beyond pure scientific research and have an impact on society. Because a healthy scientific culture definitely requires an open society where questioning authority, questioning scientific authority is valued and promoted, where people are allowed to express their opinions freely. And scientists understand that anyone from anywhere can come up with a new idea or challenge an old idea. So science promotes tolerance. And because of that as well, science promotes democracy. In scientific discourse, everyone is equal. And we encourage our students to challenge our ideas and to come up with better ways of approaching difficult problems. Science promotes democracy. It's not an accident that one of the leaders of the democratic and human rights movement in the Soviet Union, many of the leaders, among the most prominent of which was Andrei Sakharov, a prominent theoretical physicist. So let me now turn to what most people think is the main lesson of science. Not this method of discourse and behavior, but rather knowledge of nature itself. And I will cover 3 areas in science, starting, of course, with the queen of the sciences, my own field. But then going back perhaps to the oldest science, astronomy and cosmology, and ending with one of the most vibrant sciences today, where advances are happening very rapidly, biology. Science of the universe, physical phenomena, biological as well. In all of these areas, physics for the last 400 years, astronomy and cosmology for the last 100 years, biology for the last 150 years, unbelievable progress has been made in this very short time. I think it's a long time we've been doing science, but actually physics is the oldest, and that's only 400 years old, which, is like 5 lifetimes laid one after another. And the progress in astronomy and cosmology, our knowledge of the history of the universe, has all happened in less than 100 years, which is less than 2 human lifetimes. Let me start with physics. Over the last 400 years, we have discovered the basic laws of motion that we were reminded of by Dr. Salazar, and the symmetries that underlie these laws and govern all physical phenomena. In this century, in the last century, we unveiled the underlying atomic structure of matter and discovered the quantum nature of reality. And towards the end of the century, this was where I worked, we constructed a comprehensive theory of both the atomic and the nuclear forces, and identified the basic constituents of matter, and are now working, striving to unify all the forces of nature together. It all started with Galileo at about the same time this university originated, who started applying the scientific method to real physical phenomena, starting with simple objects, pendulums and rolling balls down inclined planes, discovered the regularities of motion, and understood that in order to model and explain those regularities, one needed to use mathematics. It's an incredible language, extension of human language that we have discovered, that mathematicians have constructed, and which Galileo realized is the language of physics. Galileo was shortly followed by Isaac Newton, who carried out the first scientific revolution, discovered the law of gravity, the laws of motion, and realized that the laws of physics govern the motion of both planets and apples. That the laws of physics work everywhere in the universe and for all phenomena. In the 19th century, physicists started exploring the second force of nature, the electric and the magnetic forces that were finally unified by Maxwell into a beautiful set of equations that could be summarized on a t-shirt, but explain all of the phenomena associated with electricity and magnetism and light itself, which was realized to be nothing more than a wave of varying electromagnetic field. Maxwell was the first to construct a unified theory, to unite what previously were thought to be separate forces, separate phenomena, electricity and magnetism, to a unified theory of electromagnetism. The other great advance in physics in the 19th century is understanding the laws of heat and energy and entropy and disorder, the tendency of all large systems to disorder. In the 20th century, we finally realized the goal set forward by Democritus, who stated 2 millennia ago, that all of matter is composed of point-like atoms, and that the structure of large bodies can be understood by the behavior of large numbers of small atoms interacting. And in the 20th century, we indeed verified that all ordinary matter is made of atoms, and we observed and figured out the structure of atoms, which consists of electrons revolving around nuclei, and these people here, Planck and Bohr, Heisenberg, Dirac, Rutherford, Schrödinger, Einstein, all contributed to the understanding that all ordinary matter, everything you see in this room, in the end is made of atoms, electrons revolving around nuclei, governed by strange new probabilistic laws they discovered called quantum mechanics. And based on those atoms and the force of electricity that holds the electrons in place and the laws of quantum mechanics, we have been ever since working out the properties of all the kinds of matter we see or create. new kinds of matter. The properties and the phases of all the matter that we have around us comes from, and we think eventually can be explained by, the collective behavior of atoms. The other great contribution in the early part of the 20th century was Einstein's revision of Newton's famous law of gravity. Einstein taught us that space and time is dynamical, not just an inert reference frame, but a dynamical entity that can bend and curve, and does so in response to mass and energy. And it's the curvature of space and time itself that gives rise to the deviation in the motion of particles that we call gravity. This is the general theory of relativity, and it is a serious, wonderful, beautiful modification of Newton's laws. Newton, in some sense, is wrong, was wrong. But in science, we've learned that Newton wasn't that wrong. Because if we are trying to plot the trajectory of a rocket or go to the moon, we don't have to use Einstein's equations. Newton's equations are good enough. Newton was a very good approximation to what is a more correct, better approximation to nature. But in the end, Newton is only an approximation, and Einstein's equations are probably, as I said, also provisional. We believe that they are also only a good approximation, good at large enough distances. Finally, towards the end of the 20th century, we completed what is now called the standard model of particle interactions. This is an understanding not just of the atomic force of electricity and magnetism, but the nuclear forces, the other two forces in nature. And the identification of the elementary particles out of which all matter that we have ever observed in the laboratory or anywhere on Earth is made. Those are the electron that forms the outer shells of atoms, and the nuclei, which we learned are made of something called quarks. And we are made out of nuclei that contain quarks whose names we give, up and down quarks, and electrons, but there are three families of copies with different, some are much heavier, but otherwise copies of this family of quarks and atoms. And the forces that act on these particles, we understand now. That's the force of electricity and magnetism of Maxwell. But now we also understand the forces that act within the nucleus, the strong nuclear force that holds the nucleons together, that holds the quarks within the nuclei, and the weak nuclear force that turns one quark into another, is responsible for radioactivity and the transmutation of elements. This standard model really is a theory, a comprehensive, extremely well tested, with great precision theory of all the observed forces of nature and all the kind of matter is called the standard model. It's the theory we're trying now to go beyond, but it's an incredibly successful. And I want to say a word about the strong nuclear force. That's what I was involved in working out. That's what we got the Nobel Prize for. So let me tell you a bit about that story. The nuclear force was really hard to figure out. The nucleus is very small. See it? There, I'll blow it up. It was still hard to see and to get inside the nucleus and to figure out what was going on. The only method we have is to smash two nucleons, protons together, and there's a horrible energetic collision, and hundreds of particles come out, and we try to figure out what goes on inside the nucleus that way. It's not easy. But by the time I was a graduate student, people were making progress. And shortly after, they discovered that it looked like, you did experiments which looked at the proton over very short times, so the quarks couldn't move very far. It looked like the proton was made out of funny kinds of particles that people had hypothesized called quarks, which had fractions of an electric of the charge of the electron, and no one had ever been able to pull them out of the proton, no matter how hard you smash protons together. And it was that mystery that led me to try to understand how that could be. How could these quarks move around freely at short distances, especially since no one had been able to pull them out, so they had to somehow be tied together very strongly, at least when you tried to pull them out. And in the end, we figured this out. We found a theory which had this phenomena, but it's a strange, had the phenomena that was referred to as asymptotic freedom, this phenomena that the quarks, when they're very close together, are not very strongly pulling and pushing on each other. They just move around freely. But if you pull them apart, a very strong force develops. The strong force gets stronger at large distances, weaker at short distances. That's pretty weird. And it has to do with the weird properties of the vacuum. Now, most of you probably think of the vacuum like this slide. Nothing. Boring place. Remove everything from this room, all the people and all the chairs and all the air, and you're left with, pull it down to absolute zero, you're left with the vacuum. It's just a boring place. There's nothing smooth, nothing in it. And indeed, classically, that's our picture of the vacuum. It's sort of the lowest rest energy state of the world. Not totally empty, boring. But this is totally wrong. And we've learned in quantum mechanical theories that nothing can be at rest, motionless, inert, because of essentially the uncertainty principle. So, for example, classically, a pendulum that has some energy moves back and forth, right? Its lowest energy state of the vacuum is like this, at rest. But quantum mechanically, that's impossible, because how would you know it's at rest? You have to observe it. You observe it by probing, and any probe will start it moving a bit. So it must be moving. Indeed, a consequence of that, of quantum mechanics, Heisenberg uncertainty principle, is that any dynamical object has, even in its lowest energy state, like the vacuum, has some motion. The vacuum is full, space is full of electromagnetic fields. Classically, we could turn them off. But quantum mechanically, when we probe the vacuum, we excite these fields. And it's not just the electromagnetic field, it's the fields of the nuclear force. Fields of the theory we developed called quantum chromodynamic fields. So I'm going to give you a picture based on quantum chromodynamics of what the vacuum really looks like. We can calculate its properties using the theory, or my friends who use big, massive computers can do that. And this is a picture of the quantum vacuum at the scale of a nucleon. So this is about how big on this scale a proton is. And here you have fluctuating chromodynamic fields. These are the fields that transmit the force between quarks. And you see the vacuum is a very complicated medium. All these fluctuating fields carrying energy. And in such a medium, just like in water and or different medium, the force between particles, charged particles, can vary with distance, so can it in this QCD medium. So quarks, when they are close together, can have a very weak force. That's what happens. But when you pull them apart, the force gets stronger. In fact, so strong that you can never pull them out of the proton. Here's a calculation of that. In QCD, you have a proton whose mass we can now calculate from this theory. And it's made out of 3 quarks. And when they're close together, they don't interact very much, but when you start pulling them apart, trying to get them out of the proton, this very strong force field, which is pictured here, develops, and you can never get them out. So that's QCD and asymptotic freedom. I now turn briefly to cosmology, a field whose development has mostly occurred in the last 100 years. And over the last century, we learned that the universe is much bigger than the Milky Way. We used to think just less than 100 years ago that it was just the Milky Way. We learned that our sun is only one of 100 billion stars in the Milky Way, in our galaxy, but that our galaxy is only one of 100 billion galaxies in a universe that is getting bigger, expanding, stretching at almost a constant rate. And that expanding universe came from a very small, hot, dense region that started expanding 13.7 billion years ago. I don't know whether you can see the bottom here. We know the age of the universe now to the accuracy of about 1%. So our scope has expanded enormously with modern instrumentation and observation and theory from the Earth, which is about 10 to the minus 13 light years across, a few thousand kilometers, to the solar system, which is 1 billion times larger, to the galaxy, which is 1 billion times larger than the solar system, and then to the universe as a whole, which contains 100 billion galaxies. And on the large, this is a picture based on surveys we have now of the whole visible universe. Looks very smooth, not much structure. We can also go and use our time machines. We have time machines that allow us to see what the universe looked like in the past. They're called telescopes. Light takes time to get here, so if we observe light that comes from 1 billion light years away, then it started on its journey 1 billion years ago. So we can observe the universe 1 billion years ago. 2 billion years ago. We can observe the universe all the way back to 13.5 billion years ago. And this is the first picture, the oldest picture we have of the universe as it looked 13.5 billion years ago. It was extremely, at that point it was a very homogeneous, boring gas. Structure emerged. This is the history of the universe. This is the period I was talking about. We more or less understand the expansion and the history of the universe using observation and our understanding of physics from here to today. We understand how from this rather smooth gas structure emerged as denser regions pulled on each other, collapsed, and formed stars and galaxies, and what we see today is the universe. We also believe that the universe before this period expanded very rapidly or inflated and began in what we call a Big Bang, whose origin, whose meaning we don't really know. That's where our theories, fundamental theories of physics, seem to break down, and we are driven to go beyond them. In fact, one of the most exciting and current questions for both cosmologists and people like me doing fundamental physics is to try to understand what is the Big Bang? How did the universe begin? How did time begin? What did the universe collapse and then expand? Is the universe cyclic or something even wilder? This did not used to be an area where science had much to say. It was not a scientific question, but now it is. And not clear that we can answer it, or will be able to answer it, but it's certainly an issue that is under scientific investigation. And we look for signals in this so-called microwave background, this picture of the universe way back then, of the conditions that obtained right after or at the Big Bang. We try to test our ideas. So let me now turn to the youngest science, in a way, biology. And there the advances also have been immense over just 150 years. Over the last 150 years, we've learned that life emerged about 3 billion years ago on this planet, evolved by mutation and natural selection. We've begun to understand the microscopic workings of life. We've located and deciphered the genetic code and outlined the basic microscopic mechanisms that make living cells work and discovered the cause of disease. And finally, the hardest part of biology, we have located the source of consciousness and emotion in the brain and have started to explore its mysteries. Began with Darwin 150 years ago, who based on numerous observations came up with a theory of evolution via natural selection and mutation produces all the variations of living matter. That theory has been extremely well confirmed, even before we had, as we do now, a microscopic understanding of how that works. And we've traced out the tree of life, that the history of evolution through the evolution of millions of species, most of which are extinct. We are one of the last on the scene. We are, as a species, only about a few million years old. And we've discovered, in fact, using now our genetic microscopic understanding of the code of life, we've been able to trace our history, not just our relationship to other species, but our relationship to one another. And this is an amazing story which is still being worked out. But we have learned that all of us have a rather recent common ancestor. It seems that all of us, all humans, have a common mother and a common father who didn't live at the same time or at the same place, which is possible. Now, their mitochondria structure comes only from mothers, and the Y chromosome only from fathers. And we all have a common origin in Africa about 150,000 years ago. We're all related. And we're beginning to track this detailed history of human migration through the genetic code. This lesson, I think, is extremely important and has important implications for peace. How can we fight if we're all related? We're all one family. Of course, we have lots of fights. But it's true. And I don't think it is yet truly sunk into the human imagination of how closely we are all related and what implications that should have for the way we regard each other. Most importantly, for biology as a mature science, we have begun to construct a microscopic theory, structure, and understood the microscopic structure of life. We have identified what are the mechanisms that contain the information that governs the behavior of each cell in our body, and the code being based, of course, on DNA, and the mechanism that produces through RNA the proteins carry out the structure, the functions of the cell. These microscopic mechanisms have incredible power in biology as they have had in physics, and offer us the true hope of understanding in a quantitative way the workings of life itself. We have also understood, to the great benefit of mankind, that disease is caused by other living cells, or viruses, or parasites, all of which we know how to control in principle and often in practice, and genetic mistakes, mutations, and mistakes in our code, which we are beginning to learn how to identify and maybe correct. And finally, we have located the locus of thought and emotion. And it is this brain located in our heads, which upon closer examination is a vast collection of 100 billion interconnected neurons. So we have the microscopic structure of the brain, and the problem now, an immense problem, and a fascinating one, is to figure out how thought and memory and consciousness and emotion arise from the collective behavior of 100 billion neurons. All of this understanding, knowledge of nature, has led to great control of nature, and much of it was unpredictable. In fact, basic science inevitably leads to greater control over nature, but through what are unpredictable new tools. Much of the great advances in technology that have happened over the last 4 centuries have been a consequence of discoveries of basic science. But the scientists who made those discoveries were not looking for the applications. They were driven by curiosity. They discovered new phenomena, new tools that they would never have discovered if they were looking directly for application. Nature is a lot smarter than we are. And by trying to figure out nature's secrets, we discover things that are useful, which we would not have discovered by direct attack on the problem. Somebody, once said if the English government or some government had decided to try to find new tools for imaging the human body in the end of the 19th century, applied scientists would have constructed very powerful light beams to try to see within the human body. Nobody would have had the vaguest idea about the possibility of X-rays, which were discovered accidentally by scientists looking for totally different directions, nothing to do with their eventual applications. The same is true actually of most imaging techniques in medicine, which have come from physics, but physics which was being pursued for reasons of basic research. And this technology that science has produced, of course, is of immense benefit to humankind, but also presents grave dangers. It led to the Industrial Revolution. Our ability to control heat and energy, the steam engine, our ability to control electromagnetism, which led to the use of electricity and motors and everything we have today. And more recently, quantum mechanics, this strange new theory that had to be invented to understand the workings of the atom, has applications that we all use today, like this computer or my telephone. New methods of transportation, which don't really use that much quantum mechanics, but our cell phones and our computers do. So all of this is great, and the benefits of biology have been equally great. Biology, our understanding, has led to powerful drugs that fight disease, and incredible imaging techniques, not just X-ray, but many others. So we can now see within the human body, within the human brain, and diagnose disease and many other applications of science. So much so that the human lifespan in only 200 years has doubled. All of us have 2 lives compared to our ancestors only 200 years ago. 200 years is only 3 lifespans. So we've doubled the human lifespan. All of that are the wonderful applications of science, knowledge, technology that ensues from knowledge. We've also produced, however, some unintended bad consequences like powerful and awful weapons that still threaten the extinction of our species if we ever are stupid enough to use them.